Hello again, grade 12s, and welcome to another video with me, Natasha Barton. In this video, we will be looking at question number 3 of the November 2021 Physical Science Paper 1 exam. This question deals with vertical projectile motion. Specifically here, however, we have a hot air balloon. So if you are one of those learners who immediately starts to panic when you see a hot air balloon in your physical science papers, then please stay with me and watch this video until the very end. Take down notes, because remember, the more you interact with the video, the more of the knowledge you are most likely going to retain. So displayed to the top right hand corner of your screen, you can see a little screenshot that I've taken from your formula sheet. These are the equations of motion. And very often in this section, or most often in this section, we make use of these equations of motion. I'd just like to remind you that this is velocity. It's the final velocity. This is initial velocity. And both of these values are vector quantities. So, grade 12s, when you substitute into these formulae for initial or final velocities, you need to take signs for direction into consideration. A is for acceleration, and acceleration is a vector quantity as well. So if you have chosen down to be negative and you have an object in free fall, then you know that the 9.8 meters per second squared, the gravitational acceleration, you're going to substitute into this formula as negative 9.8. Over here we have time. Time is the only scalar quantity in these formulae, so here we don't need to take direction into consideration. But lastly, in these formulae, you're going to see, well, not change in x since we're dealing with projectiles, but rather change in y. And this change in y is for displacement. So depending on where you take your zero or reference point to be, you need to take direction into consideration when you substitute into these formulae. Over and over again, I see learners forgetting to substitute into the formulae the plus and minus signs for their vector quantities. Please don't forget this, because it may cost you a huge amount of marks. Let's now take a look at question number 3. Now, question number 3 begins with a statement which says, a hot air balloon is moving upwards at a constant, unknown speed. Before we move along and see what the questions ask, let's analyze this statement. We know that the hot air balloon is moving upwards, but also more importantly, they say it's moving at a constant speed. And from Newton's laws, you should know that a constant speed implies that the net force acting on this air balloon is going to be 0 newtons. And if the net force is 0 newtons, it means that the acceleration is going to be 0 meters per second squared. So it is important to analyze these statements because they give us useful information. Now, question 3.1 says, is the hot air balloon in free fall? Choose from yes or no, and then give a reason for your answer. You're going to get 1 mark for stating whether your answer is yes or no, and then 1 mark for the reason. Let's start off by remembering what the term free fall means. From your exam guidelines, you'll remember it says an object is in free fall, or we define free fall as motion during which the only force acting on the object is the gravitational force. Now, for this hot air balloon, is the only force acting on it the gravitational force? The correct answer is no. And that is not because the hot air balloon is moving up, not necessarily because of that, but rather because, remember, we found out that the acceleration is 0 because the net force on the hot air balloon is 0. When an object is in free fall and the only force acting on it is gravitational acceleration, then the acceleration should be equal to the gravitational acceleration, which is 9.8 meters per second squared downwards. So since the acceleration is not 9.8 meters per second squared, we know that the correct answer is no. Now we need to give a reason. We can say the gravitational force is not the only force acting on the balloon. There are other forces acting on the balloon, and for that we can get our second mark. Or you can say its acceleration is not 9.8 meters per second squared. Instead, the acceleration is 0, and that could get you your mark for your reason. Or you can say it has a constant velocity and therefore no acceleration, and that will give you a mark for your reason. So you have 3 options here as possible reasons, and that's going to get you your 2 marks for question 3.1. Fortunately, we have been provided with a diagram in this question or on our question papers, so it's important that we make use of this diagram to help us understand the situation. We have the hot air balloon. We can see indicated on the sketch that the hot air balloon is going upwards. But below this diagram, we have some more important information. They say when the balloon is 200 meters above the ground, a small stone A is dropped from the balloon. See the diagram above. So over here on the diagram, they have indicated A. And as you can see, it is dropped at 200 meters above the ground. Another small stone B is dropped 5 seconds later from the balloon, while the balloon is still moving upwards at a constant velocity. So we know that the second stone, stone B, is probably going to be dropped when the balloon is higher up in the sky. And therefore, I'm going to go and draw B over here, right? When the hot air balloon is a bit higher, B is going to be dropped. They then say stone A strikes the ground with the speed of 62.68 meters per second. So we know V final of A when A hits the ground is going to be 62.68 meters per second to the negative 1. Ignore air resistance, and 3.2.1 says calculate the speed of the hot air balloon. Now, we don't have a lot of information given to us in this question, but we have the most information about stone A. We don't have a lot of information about the hot air balloon. We don't know, for example, what its mass is, right? So, if we look at A, we know that this stone is going to start off with an initial velocity, which is equal to the velocity of the hot air balloon. So this object is a projectile. It starts off with an initial velocity that is not 0. Although they use the term dropped, we know that since we are dealing with a hot air balloon, the initial velocity of the stone will not be 0, but will be equal to the speed at which the hot air balloon is traveling. Please do not forget this very useful information. So for a certain amount of time, the stone A is going to move upwards. Now I'm exaggerating this diagram. Then it is going to turn around and travel downwards, and it's going to hit the ground. Of course, it doesn't actually travel so far up. That is why we actually don't normally see this happening, and that's why it's so difficult to imagine in our minds. But we still know that for the stone A, when the stone reaches its maximum height above the ground, we know that its velocity over there is going to be 0 meters per second. And we're going to write that down because this is useful information. Since this stone starts off with a velocity equal to that of the hot air balloon, it may be useful for us to use or to calculate its initial velocity, because if we calculate its initial velocity, then we can calculate the velocity, or the speed rather, of the hot air balloon. Now we have this information. We know that stone A will have a displacement. So remember, displacement is the distance or the shortest measurement between its final and initial position. So stone A, although it moves upwards, remember its displacement is this 200 meters. Okay. So what we need to do is we need to decide on which direction we're going to take as positive. That's one of the things we need to do. I'm going to go ahead and choose up as positive. Okay, since the stone starts off going upwards, I'm just going to stick to that. But if you choose down as positive, please be consistent about that. If we choose up as positive, it means that the final velocity is going to be negative, and we're going to go and fill that in. We also know that this stone, once they drop it or once the person lets go of it, it is going to be a projectile, right? And the only force acting on it is going to be the gravitational force. Therefore, its acceleration is equal to the gravitational acceleration. Since up is positive, we know G, or A, is going to equal to negative 9,8 meters per second squared. When you write down all of these values, remember to include the directions so that you don't forget to substitute direction into your formulae. So now we go to a formula. We go to our equations of motion, which we're going to find on our formula sheets. We are looking for speed, the final velocity, the initial velocity of a stone A. For stone A, we know its final velocity, we know its acceleration, and we know its displacement. We're therefore going to go ahead with this formula. We say V final squared is equal to V initial squared plus 2A change in Y. Please be careful. I often find that when learners write down this formula, they tend to leave out the square. Please be very careful and don't make careless mistakes like that. The final velocity we said is negative 62,68, and we remember to square it. We do not know the initial velocity, so we leave that as VI plus 2. The acceleration is negative 9,8 because we chose down as positive, and the displacement is going to be negative 200. What we have done is we have taken this position where stone A starts to be the reference point or zero position. So since the stone's displacement is below that point, the 200 meters is negative. We're taking direction into consideration because change in y is the displacement, and displacement is a vector quantity. Now we manipulate this formula and we solve for V initial, and we find that V initial, after taking the square root, etc., is going to give us a final answer of 2,96 meters per second. They asked us, although this over here is actually velocity, or VI stands for velocity, we're going to leave it as is because we are calculating speed, and speed is a scalar quantity that requires no direction. We're going to allocate the marks, or marks will be allocated as follows. You're firstly going to get a mark for your formula. Then you're going to get a mark for your substitution, and finally, you'll get a mark for your final answer. As you can see, and I know I keep emphasizing this, I do apologize, but please remember to take direction into consideration or you're not going to get your marks. You are more than welcome to calculate the speed of the hot air balloon by making use of other formulae. For example, you can make use of the principle of conservation of mechanical energy. You can make use of the work energy theorem in general, or simply the work energy theorem. If you'd like to try these, please remember to make use of the exam guidelines to see if you have performed your calculations correctly. Before we move on to question 3.2.2, I would like to take stone B, which I drew on the right hand side, and move it to the left hand side just to avoid any confusion that my sketch may have caused. Stone B, like stone A, is going to be dropped from a moving hot air balloon, and therefore stone B is going to move upwards for a little while, and then it's going to accelerate downwards towards the earth. It is in free fall once it has been dropped from the hot air balloon, but it's a projectile. And we say it's a projectile because it also starts off with an initial velocity. Its initial velocity is equal to the speed or velocity of the hot air balloon. Now, question 3.2.2 reads, we need to calculate the time it takes stone A to strike the ground. Before we answer this question, I would like to add onto the information that we have the new information that we just calculated at 3.2.1. We now know that the balloon, which is traveling at a constant speed, has a speed or velocity given as what we calculated at 3.2.1. That is 2,96 meters per second. We know that ball A's initial velocity is 2,96 meters per second as well. And we know that ball B's initial velocity is also going to be 2,96 meters per second. Now we would like to know the time that it takes stone A to reach the ground. My apologies if I said ball instead of stone at any point. We would like to calculate this time. And we know that we can make use of an equation of motion. But there is so much information that we now know about stone A that there are many different methods you could have used or may have used to calculate your answer to this question. So if you go to the exam guidelines, you're going to see there are 6 different acceptable methods that you could have used. I'm going to show you only 2 of these methods. The rest you're welcome to go and check or try yourself using the exam guidelines. I'd like to remind you that we have chosen to take up as positive, and we must be consistent with this. Stone A first travels upwards and then travels downwards. We can use the very first formula in or on the formula sheet, the first equation of motion, to calculate the time that it is going to take stone A to travel to the ground. We say V final is equal to V initial plus acceleration change in time. The final velocity is negative 62,68 meters per second. Sorry, we don't need to substitute into this the unit. The initial velocity we calculated to be 2,96. We substitute this value into the formula as a positive value because it is the velocity when the ball or the stone, starts off, right? So when it's dropped from the hot air balloon. Then we say the acceleration is going to be negative as well because we chose up to be positive and we don't know the time. If we manipulate the formula and solve for time, we find out that the time it is going to take this stone to travel to the ground is going to be 6,70 seconds. This is one of the methods that you could use, and you're going to get 1 mark for your formula, 1 mark for your substitution, taking direction into consideration, and 1 mark for your final answer. Now, a method that is very popular amongst learners is to, instead of calculating this in 1 step, do it in 2 steps. So I'm going to show you the alternative method, or at least one of the 5 other methods. So we know that when stone A reaches its maximum height, its velocity is going to be 0 at this maximum height. That's what we know. V is going to equal to 0. When it gets to the ground, we know its final velocity. So what we're going to do is we will calculate the time it takes for the stone to travel to its maximum height. And then when we are done with that, we can calculate the time it takes for the stone to travel down towards the ground from its maximum height. So this is a 2-step calculation. We now say V, so we're going to start off with the first part of the calculation. You don't need to label this part 1. I'm just doing so that you can see exactly what I'm doing. So this is part 1, right, which we're going to calculate the time over here. We say V final equals V initial plus a change in time. For this movement or this motion, we know the final velocity is the velocity at the maximum height, that is going to be 0, is equal to the initial velocity is 2,96. The acceleration is negative 9,8 because we take direction into consideration. And when we solve for the time, we obtain an answer of 0,3 seconds. that is the time. This is an S, not a 5. So 0.3 seconds. To calculate or travel, through this height, we know the stone is going to take 0.3 seconds. Now we're interested about the other side. So this is part 2, the part that I have highlighted in green. We would like to find out how long or how much time the stone is going to take to travel from its maximum height all the way to the ground. At its maximum height, that is for this motion. So for this downwards motion over here, we now know that this at the top is the initial velocity, and when it strikes the ground, that will be the final velocity. So we have negative 62.68 is equal to the initial velocity is going to be 0 plus negative 9.8 change in time. When we manipulate the formula, we obtain an answer of 6.4. So change in time, or the time, is going to be 6.40 seconds. All right, if you just say 6.4, that will be okay. Now we know that the stone is going to first travel upwards, and then it's going to travel downwards. And the time it takes for each of these motions, if we add them together, that is going to give us the total time. So we say, therefore, the total time, if you would like to call it that, is going to equal to 6.40 plus 0.3 seconds. When we add this together, we get 6.70 seconds. And this answer is exactly the same as the answer that we obtained on the left. So for such a long calculation, you're not going to obtain any extra marks. You're going to get 1 mark for your formula, 1 mark for substitution, and 1 mark for your final answer. That is your 3 marks for this question. Remember, there are now 4 other methods that you can use. So try other methods and then go check with your exam guidelines to see if your answer, or your method rather, is correct. Your answer should be exactly the same, 6.70 seconds. We now move on to the last problem in this video and in this question, which is question 3.3. It says, on the same set of axes, draw position time graphs for both the hot air balloon and the stone, from the moment the stone is dropped until it strikes the ground. So the graph must start off at a time 0, that is when the stone is dropped, and it's going to end with the time that we calculated or found that the stone is going to take to reach the ground, and that is the 6.70 seconds. Remember, we are dealing with stone A. So already I'm going to go to my graph, and I'm going to include on that graph the time of 6.70 seconds. Although it was actually not necessary to indicate values on this graph in order to get your marks, I'm going to do so anyway so that you understand why I am drawing it the way I am. Now we go on and we see that the question says, use the ground as 0 reference. That means the ground is the 0 point. Label your graph balloon and A so that the marker can distinguish between the 2 graphs. I'd like to remind you that right at the beginning of this question, they gave us a sketch and information beneath that diagram. They said stone A starts off at 200 meters above the ground. So that means that on this graph, we're going to start off stone A and the hot air balloon at 200 meters above the ground. We're going to start off with the graph for the stone. We know that the stone is going to move up for a while. It's going to slow down, and then it's going to move down and hit the ground. This diagram is not drawn very well. Let me try again. This is the best that I can do. I'm sure that you can do better though. We know that the hot air balloon is going to continue to travel upwards at a constant velocity. When you have a position time graph and you would like to indicate constant velocity, we show it using a straight line. So we know that the hot air balloon is going to continue to travel upwards. And again, as I've mentioned, I'm not drawing this very well. We actually need to do something like this. Okay, I'm going to remove my label for now so that it doesn't confuse you, my heading. Right, but that over there is going to be the graph for the balloon, because the balloon is going to continue to travel upwards at a constant velocity. As you can clearly see from this graph, right, they both end at the same time and they both start off at the same time. You're of course not going to make markings like this on your graph, but it is important, very important, that you label the graph. So you're going to say this is the balloon, and the graph that I've drawn in blue, that is stone A. They just said we need to call this A, so you're going to label that A. You're going to get your marks over here for the correct shape of the graph for stone A. Very important, stone A must start at 200 meters. It must not start on the ground. So that's 1 mark for that graph. You're going to get 1 mark for the shape of your graph for the hot air balloon, and it must also start at 200 meters as we have done over here. The gradient of the graph for the hot air balloon, we can see over here, is higher than that of stone A, and the reason is because stone A is slowing down while the hot air balloon continues to travel at a constant velocity. For showing that difference, you're going to get your 3rd mark. And lastly, you're going to get your graph for the fact, your mark for having them start at the same position and ending at the same time. That is your 4th mark. You can of course go see your exam guidelines to see the more accurate version of this diagram, but this brings us to the end of this question that is out of 18 marks. Thank you so much for joining me, and of course if you've reached the end of this video, thank you so much for your dedication and hard work. I do hope that it pays off. In the next video, we're going to look at a question that involves momentum and impulse. We're going to be dealing with those elastic and inelastic collisions, etc., when we look at question number 4 of the 2021 exam paper. I hope to see you there.